Let's continue writing this Starfield program. First of all, some optimizations. Number one is that the radius here goes from 16 to 0, but because of processing's ellipse function, the radius is actually the diameter, so we should divide this by 2 to get the consistent looking output. Additionally, you'll notice that it ran very slow last time, so we can fix that by changing the line to not be anti-aliased, because that is apparently a very expensive computation. And as you can see, it now runs buttersmooth. There's still this strange white rectangle that shows up every once in a while. You might have seen it earlier. It only shows up for a frame or two. But when it shows up, it is very jarring. I'll see if I can't get it. There it is. You get the idea. Okay, and then the other thing that we have to do today is write that translate method. So this requires a lot of matrix math. We're going to go ahead and write in here canvas.reset matrix, canvas.translate width over 2, height over 2. So these are the functions that we're going to be writing. Let's start with reset matrix because that's the easiest. And what we're going to do is we're going to have a static variable called matrix stack. It's going to be behind a read-write locks for multi-threading purposes. Reset. And again, we haven't written much of the code that's required to make this work. Then we can write translate. Dx, dy, matrix stack, write, translate, dx, dy. Now let's start writing the matrix stack code. Matrix 3, we are going to be using 3D matrices to represent the 2D transformations. This is consistent with how in three-dimensional computer graphics you use four-dimensional matrices to represent transformations. So data is an array of 9 floating point numbers. And we're not going to have an explicit new method here. We're going to represent our transformation matrix using transformations on the identity. So identity and we all know what the identity matrix is for 3 dimensions, hopefully. That. Translate takes self-mutably. Dx, dy. Actually, how about we make this return a new matrix instead? And we're going to make a private function new here, which takes in the data. Just like that. So instead of translate here, it's not going to take anything in besides dx and dy, and it's going to say translation instead, because this is a translation matrix. And we're just going to define generic matrix multiplication in order to compose transformations. So it's going to be the identity, except here we put dx, and here we put dy. Just like that. We can also define a rotation matrix. Self, new, So here we're going to have cosine of theta, negative sine of theta, sine of theta. Oh, here this is actually going to be 0. Sine of theta positive. Cosine of theta again, and another 0, and then more zeros, because this is the third row, and it's just going to be identity. And finally, we can have a scaling matrix. Scale vector. Do. No, let's not use a vector. We'll just say it's x and sy. It's x, 0, 0, 0, sy, 0. Basically, we're taking the identity matrix and replacing the x and y parts with sx and sy. There we go. And just for consistency's sake, we'll go up here, say self new, just like that. And we have a matrix. Now we need a multiplication method. So we will say impl mul for matrix, stating that we can multiply matrix 3's by each other. And we will say self new. And now this is a quite complicated formula that I'm going to go ahead and look up. You can see that this is not the first time that I've looked this up. So here's the formula. I will just keep that down there. Maybe zoom it in a little because I can't see it that well. Just keep it right there. And we'll translate it into code. A11B11. So that is self.data 0 times other RHS.data 0 plus self.data 1 times RHS.data 3. And it's 3 because 0, 1, 2, 3 plus self.data 2 times RHS.data 6, and so on. I'm just going to copy and paste the rest of this. This is not 1, it is 3, and this is 6, because we are going 3 at a time. This is 4, this is 7, and this is 8, or this is 5, and this is 8. And there we go. That is three-dimensional matrix multiplication. Very tediously done, but we never have to do it again. So we will say, let me make this bigger, that we are done with the matrix. So let's also add a matrix stack. it has a vector of matrix 3. And it's going to start with the identity matrix on top. This is important. I believe that works, yes. We have a push method. Just like that. We have a pop method, which does what you expect. We will have a translate method. And we will say it's equal to, well, let's see. And we are unwrapping here because we are saying that as long as you push and pop the correct amount of times, it will always have at least an identity matrix on top. That's why we start with the identity on top. And we're going to clone it just because I know that Rust is going to complain a little bit here. So we'll go to matrix and derive clone. There we go. Now top is a matrix 3. Equals. We're going to dereference that. It is going to be left multiplying the top. Matrix 3 translation dx and dy times top. This should compile, and it seems like it does, but I'm not entirely convinced yet. You know what? Let's get rid of these errors over here and create a matrix stack variable. So we're going to need some more crates. We're going to need parking lot for the synchronization primitives that are a little bit easier to work with than the standard libraries. And we will add lazy static. There we go. Hub static ref matrix stack. You know what? Let's not make it public. Let's make it internal to the crate. It's a read-write lock of matrix 3, matrix stack, excuse me. And we're going to initialize it with just a basic matrix stack, which, keep in mind, has the identity matrix on top still. So there we go. We have matrix stack. If we go back to lib.rs, we should be able to import it now. Let's see what's going on. Consider importing. Yes, that's what I want to do. All right, we'll do it manually. There we go. We've imported the static. There's no reset method. That's okay, we just forgot that one. And that is taking itself mutably. Self.stack equals, we'll just reset it like this. There we go. It says consider adding a default implementation. So we will. Why not? Can't hurt. And we'll just defer to the default implementation up here. There we go. Unfortunately, I can't do that for reset because we're just, we can't throw away the instance and create a new one. We have to modify the instance. But that's all right. And it looks like this method actually does compile. So let's continue writing more. Rotate. Keep in mind that theta is in radians. Since this is the part of the public interface, I will go ahead and add a comment here. Or maybe we'll do one better, have some self-documenting code. Top, well, let's just copy paste this code. This is now a rotation matrix. Radians. There we go. One last time, let's write a scale method. There we go. We've now implemented a matrix stack. We have a static one. So we can continue adding some more methods to the canvas here, saying rotate. So this is the actual public interface that we'll actually be using, since we won't actually have any matrix stacks in the user code. So realistically, I could go back and rename that to theta, but why not? Let's keep it as radians. I think that's more clear. Let's implement these methods. Scale. And there we go. We now have a way of saying you can reset the matrix, you can translate and rotate and scale. There's one more method that we need here, or two more, I should say, to make this a very powerful implementation. And basically, if you've ever heard of the Logo programming language, we can implement turtle graphics using just matrix math and drawing lines of unit length. But we're not really going to bother doing that. We're just going to use it as a tool to make other math easier. So we'll say push matrix and pop matrix. These are basically save and restore commands, because push matrix, and I've actually messed up the matrix stack implementation, but we'll worry about that in a moment. Now, in order to make this function as a save and restore, we need to edit the push method here. Instead of pushing the identity matrix, let's push a copy of what's on top. Let's say top. Self.top.clone. And there we go. Now we have save and restore functionality, we have translation, rotation, and scaling. Now, unfortunately, we need to re-implement the drawing methods, or at least wrap them, in a way that takes this matrix stack into account. So we will say as a bonus, we can use vector2. And we can add the color in like that. Vector2 is the center. Radius is a F64, or floating point number. Let's implement these. So we will say let start equals point new start.x as i32, start.y as i32. We're just going to convert into the STL version of this stuff. End equals point new end.x convert to i32 and y convert to i32. Now we can say self.drawLine start end. Map error, STL error, draw. And we're going to return a result here of nothing or an STL error. Let's add that to the trait as well so they don't get yelled at. There we go. We'll return OK at the end, and we will set the draw color because I forgot about that part. Embarrassing, I know. And there we go, that's the drawLine method wrapped. And in fact, I'm going to use the SDL2 GFX version of this. X1, Y1, that's start.x as I16, start.y as I16. We don't need to set the draw color anymore. We don't need to do that anymore because we're already casting anyway. Let's do a filled circle. And in fact, let's just do that. Just return the result like that. What could possibly go wrong? Center.x as I16, center.y as I16, radius as I16, color, map error, and again we'll just return it directly. And there we go. Draw line, fill circle. We'll add more methods to this as we continue, but for now this is all we need. So let's go back to star. Instead of line, we will say draw line. We don't have to do any of this casting. PX, PY, SX, SY. Expected 2 arguments, found 3. What's wrong here? Ah, we're not using the trait. Use the trait. Still complaining that we have a mismatched argument count. Unusual. Maybe I shouldn't call it draw line. I'll call it extension draw line. Extension fill circle. Just to make sure that we don't have any collisions, because that seems to be not kosher. Does that work? It does seem to. And this is no longer necessary because we can just do it like that. And again, we will go here, canvas.x fill circle, vector 2 sx of sy, or and sy, r, and color is white. This is looking a lot cleaner. And if we go back to main, we are translating and resetting the matrix every frame. Important. Let's run it. Well, that's disappointing. Oh, you know what? That makes total sense because I forgot to actually translate x and y here. So let's add a method here for multiplying the matrix by a vector. Can't believe I've done this. This is so silly. You know what? We'll do it as a method instead of overriding the operator. We're going to say that it's an implementing as ref because sometimes I want to pass an own vector here and I don't want to be like forced to put the ampersand. That's why we're doing that. So let's see. We need a three-dimensional vector actually in order to do this math. Or we can just throw it away and use vector 2's all the way. So the x component is self dot data 0 times v dot x plus self dot data 1 times v dot y plus self dot data 2 self dot data 3 times v dot x self dot data 4 v dot y self dot data 5 times 1 implicitly. And there we go. And what's wrong here? Is it private? Oh, we have to use as ref. Let's just do that. Simple enough. There we go. I think we are nearly done here. So let's say let start equals matrix stack dot top dot transform start. Let's also implement as ref here, or require implementing as ref, so that it can be on a value or a reference. As ref. And let's change that in the trait as well so that we don't get yelled at. Make sure that compiles. Looks like it does. Let's make the top function here public. No reason not to. Oh, this is read. Transform. Let's just pass start in like that. That looks like it works. End equals matrix stack top or read top transform end. Now we are transforming the points correctly. So let's see if that works first of all. Oops. Asref is not implemented for that. Well, that's silly. Let's implement that. I mean, personally, I think that this should be auto-implemented, but what do I know? That's the implementation. Wow. And again, let's abstract. These are all introducing generics, and it may hurt compile times, but I don't care about compile times. What I care about is, does it work? So let's see, we're going to transform the center in the same way here. Just like that. And I think we're ready to run it now. Oh, that's so cool. Now we have a properly functioning star field. So besides those strange rectangles that keep showing up, I think we're done here. Yeah. All right. So that wasn't too bad. That was a bit of an adventure in matrix math for those of you that didn't do that before, I guess. Bit of fun, for sure. All right, that's the very first Coding Train episode complete. And it took me only 2 episodes to start writing the framework for it. But don't worry, future episodes will start getting faster and faster as this framework evolves and becomes more helpful, as SDL helpers should be. And you can probably think of some optimizations here. So if you think of any, please feel free to put them in the comments, implement them yourself, whatever you want to do. All right. Well, thank you guys for watching the video. See you in the next one.